Hey, this is Jason Clark here at South Dakota State University, and I'd like to welcome you back to our Soil Health and Nutrient Management section of the Master Gardeners class. For a quick review, we'll go over the outline for the class. So as you can remember, these are the different topics that we'll be covering in this class, in this section anyway. And to this point, we've covered these ones highlighted here. And today, in this video, what we're going to go over are these three sections here. We're going to review soil biological properties, soil chemical properties, and essential plant nutrients. So let's go ahead and get started. First, biological properties. Biological properties, when we think of these are the living properties of soil. Soil itself is not living, but there are living organisms inside of that soil. So when we talk about biological properties of soil, we're talking about the living things inside of soil. So first of all, there's things like bacteria, fungi, we have worms, and insects. And if we want to classify these into two different groups, what we usually will say is we have the microfauna, or that microbial group, the really small things we can't see very well, such as bacteria and fungi. And then we have the mesofauna. These are worms and insects, the larger ones that we can see. And they both perform a very vital and important work in soils. So if we look at the microfauna and some of their essential functions, first and foremost, these organisms are helping to decompose organic material in the soil. They also help to recycle nutrients, and they form beneficial root association. So if we look here at this picture of this fungus here, and here we have a plant root in this area here, and we also have two other plant roots coming down here and here. And we can see the plant roots, an extension of them, there's all these little offshoots here. This is a fungi called a mycorrhizal fungi that's connecting this plant with this plant, and also it's expanding the area in the soil the plant can explore to get food, such as nutrients and water. Specifically, phosphorus is usually a very important component of all this. But there's also a lot of bacteria and microbes that really help with this decomposition and recycling of nutrients. That is a really vital part that they play as well. So as far as the mesofauna goes, some of their duties are, of course, decomposition of organic material. They help improve drainage. So as we can think, worms and a lot of insects, ants and others, they make burrows down in the soil, make holes, and what can happen there is that the water can then follow those channels that the worms and other insects make, and also roots can as well, so it helps improve drainage and things like that. But it also is improving soil structure, because as these worms and insects, as they eat food, they release it. They usually have a sticky substances, such as around the worms, that's there, and that sticky substance acts as a glue for these different sand, silt, and clay particles to come together and form the aggregates or the structures, such as granular structures that we talked about in our last video. So these biological properties are all very important for our soils. To have a healthy soil, we need different proportions of each of these different biological properties in there. So next is chemical properties, and there are several different chemical properties we'll spend a little bit more time on. Some of the important ones are organic matter content, pH, nutrient retention, meaning how well that soil can hold on to nutrients, especially positively charged ones that are called cations. And examples of that are potassium, calcium, have a positive charge. Another one is availability of nutrients. So there are nutrients in the soil always, but that doesn't mean those nutrients are readily available for plants to take up. So we have a measurement of that as well. And these are all different measurements that we can measure every couple, 2 or 3 years to see where our soil is at. Are they improving? Are they not improving? Things of that nature. So first of all, if we look at soil organic matter, and this is something we'll talk a lot about in this soil nutrient management section. Some of the basic attributes of organic matter we're looking at is there tends to be a fibrous substance. If you think of compost, or you think of that peat that you may mix in some of your containers, it's very fibrous, it's very lightweight, and that allows it to really absorb water on it as well. And because it has lots of little absorbing areas, it's also very what they call chemically active, which means it attracts and it retains cation nutrients, those positively charged nutrients. Because soil organic matter tends to have a negative charge to it. So it's like that negative magnet that we talked about earlier that's pulling and holding on to those nutrients. Another one is soil organic matter is kind of a food source. It both provides food and shelter for different microbial communities. And then another area is that it binds mineral particles together. It almost acts as a glue in some areas. So it enhances what they call aggregation. So it takes those small particles and brings them together to form that granular, that blocky, that angular structure in our soils. And because it's kind of fibrous in nature, it actually helps to improve the drainage of fine textured soils, creates some larger pore sizes. So we don't just have those small pore sizes from clay particles, but we have some larger ones as well. And of course, people like to put a value on things, so you can kind of an offhand value. We can use this for every 1% of organic matter in your soil. It's almost worth around $500. So if we look at our next soil chemical attribute, we're going to look at pH. And what pH is measuring, it's measuring the acidity or alkalinity in the soil. And if we think about our pH range, it's a good representation here is that it's on a scale from 0 to 14, with 7 being neutral. Things less than 7 tend to be towards more what we call acid. Soils above 7 tend to be what we call more alkaline soils. If we want to look at some examples of some everyday items to see how acidic or basic or neutral they are, where they fall on this pH scale, you can think of battery acid as very acidic, very corrosive. You think of our household vinegar we use for cleaning or cooking, that's around a 3. Rainwater is a little above 5, below 6. Pure water, so no other elements in there but H2O, is neutral. Baking soda, close to 9. And then our household cleaner ammonia are very basic, have a lot of alkalinity to them, so they would be around a 12. And what pH is really measuring, if we want to look at the nitty-gritty of it, we can see here it's measuring the negative log of the H+, and that H+ is the hydrogen ion in soils. It's positively charged. And because it's negative, it's kind of an inverse. So the more positive charges they are, the lower the pH. So if I have lots and lots of hydrogen ions in our soil, then we're going to have a lower pH because it's a negative log. If we look at this kind of in a table form here, it can kind of show us in this column here we have our hydrogen ion concentration. So we start here, we have a pH of 10 to the negative 4th, which is a pH of 4, going from 10 up to the 10 to the negative 8, which is a pH of 8. So you can see the concentration of hydrogen ions in a pH of 8 is much lower, many more decimal points compared to that of a pH of 4. And the reason that a pH of going from 4 to 5 is such a big difference, as you can see, we have a tenfold difference going from 0.0001 to 0.00001 moles per liter, and that's just a concentration variance. So if we go from 4 to 5 pH, that's a big distance to travel. So normally when we're talking pHs, we usually go to the tens place. So we're looking at 4.5, a 5.5, a 6.5, a 7.5, things of that nature. So pH is important not only based on how many hydrogen ions are in the soil, but it also influences the availability of nutrients. So if we look at a chart right here, we can see on the top of our chart we have our pH. We have a pH going from a 4 to 4.5 up to a 9.5 to a 10. And so we know here, higher the pH, we're looking at more strongly alkaline. Near 7, we're looking at neutral. Below that, we're looking at more acidic. And as we can see here, these different nutrients, those areas, the larger blue areas, those are more available. And as the bar gets smaller, it becomes less available. So if we look really quickly, we can see that these top nutrients are fairly available in that 6 to 7.5 pH range. They're really highly available, and some go a little bit more. And if we look at these nutrients below here, which tend to be metals of some sort, iron, manganese, boron, copper, and zinc, These tend to be more available at a lower pH, so that 5 to 6.5 range is where plants can take them up really easily. If you get a lot higher than that, you start to get over in this range here where they start to become less available. However, if you get too low, you start to get these nutrients up here that become less available. So a lot of times what we're looking for is kind of that sweet spot. So we look here in this green circled area, it's really that 6 to 7 range where we have both those metal nutrients that we need as well as these other ones such as nitrogen, phosphorus, sulfur, magnesium that plants also need. So usually when we're looking at soil pHs, we want to be in that 6 to 7 range. However, there are some reasons that we may want to be less than that or more than that depending on what we're growing. So again, just as we've talked about before, just barely, that pH affects the availability of essential nutrients because of different chemical reactions that are going on in the soil. And it also influences crop productivity. We'll see a few figures here upcoming to see at what ranges plants can grow. Because a lot of plants can grow from a wide range. I mean, even from 5-6 up to 7-8 pH, they're still growing well. However, there are some plants that only have just a very, very small range of pH where they can grow. And we'll look at some reasons for that in a minute. So it also does affect microbial activity. Some microbes work better at lower pHs, some work better at higher pHs, but for the most part, that neutral pH is really kind of the target area that we're looking for. All right, so we can see here on this figure that we have here, we have our different plants on this side of our chart, and then on top, we have our different pH ranges going from 4 up to about 7.5. And as we can see pretty simply here, the different plants, the areas in green are those areas that plants like, that they can grow well in. So you can see there are different areas for different plants. And if we look at some loose classifications here, we can see that if we look at some loose classifications of our plants over here, we can see that we have our fruits up at the top, our vegetables kind of here in the middle, and then we have our flowers down here at the bottom. And generally speaking, they all tend to like that, about that 5.5 to 7 range, that 6 to 7 pH we talked about earlier. However, there are some that are a little bit different. So look here at our blueberries, they tend to like the pH around this 5.5 to about 5.7 range. If we look at our sweet potatoes and our white potatoes, they also tend to like a lower pH soil. And then if we look down here at our flowers, we see that azaleas as well as hydrangeas, they also like that lower pH. And here if we move on to our lawn and tree pH ranges, we see that our grasses, that 5.5 to 7 range, so a very wide range of pH. And then our junipers, pines tend to be a little bit lower pH. They like that. And forest soils tend to be lower pH, which is why pine trees tend to like that lower pH as well. If we want to look at this next one, we're going to look at the field crops that tend to grow. And here we can kind of look down here and see some general trends. Again, that 6 to 7 range, most crops fall in there at some point. However, there's a few that tend to like a little bit lower pH, a little bit higher. Here we can see that alfalfa, as well as sweet clover, they tend to like the area over here in that higher, even going up to that 7.5 range. And there are several different reasons that plants do like high or low pH, not only for reasons of growth or nutrient availability that we've seen so far, but for example, if we look at potatoes, they actually like a lower pH because it restricts fungal pathogens. If you talk to potato growers, a lot of times they have problems with fungus in their potatoes. So that lower pH tends to restrict the growth of fungal pathogens, which then helps our potatoes grow well without worrying about disease. Blueberries and cranberries also like a lower pH, and that really goes to iron availability. If we remember back at our previous figure, we saw that iron was a micronutrient metal, and metals tend to have a greater availability at lower pHs. So if the crop or the fruit needs more iron, it's going to like in a more acidic environment where that iron is more available. Azaleas, as well as hydrangeas, also like that low pH because of that iron availability, which helps with that blue color preference for hydrangeas and that iron availability for that nutrient that they need. Legumes, on the other hand, they like high pH that I showed you recently, And they do that because legumes tend to make this deal with some nitrogen fixing bacteria, and that bacteria makes an agreement that you give me some food, then I'll work to take nitrogen that's in the atmosphere and convert it into a form that the legume can use to grow. But the bacteria that make this deal with legumes, they tend to like higher pH soils because that higher pH lessens the oxygen in the soil, so then it makes it so those bacteria can function better. The next thing we're going to look at is cation exchange capacity. And just like looking at nutrient availability or pH or soil organic matter, this is a measurement that helps us know kind of our capacity of our soil to hold nutrients. So we look at the definition here. The definition of cation exchange capacity, or CEC, is the capacity of the soil to attract positively charged ions or nutrients to negatively charged soil components. So that's our awesome definition there. So what does that mean? So when you think cation exchange capacity, what I want you to do is I want you to think magnets. We've all played with magnets. We know they have positive charges, negative charges. Positive, negative charges attract. Positive plus positive repel from each other. Negative and negative repel from each other. So that's kind of the similar concept here. So our soil particles tend to be negatively charged. So if we say this ball right here, this magnet, represents a negatively charged soil particle. So what that negatively charged soil particle is going to hold on to is going to hold on to positively charged things in the soil. And what tends to be positively charged in the soil are some nutrients. We'll see some nutrients in a little bit that are positively charged, but things like potassium and calcium are positively charged nutrients. So they are attracted to negatively charged soil particles. So we can think of these sticks here that are connected to the balls as those positively charged nutrients. So the more negatively charged balls or soil particles that are in the soil, the more positively charged nutrients that soil can hold on to. And that's cation exchange capacity, is the amount of those negatively charged balls in the soil. So there are several different components of the soil that tend to have a little bit more negative charges to them. And those are clay minerals and organic matter. They both tend to have a lot of negatively charged surfaces on them that positively charged nutrients can be attracted to and hold on to. So below are going to be some examples of some positively charged nutrients. So K plus is potassium, NH4 plus is ammonium, Ca2 plus is calcium, Mg2 plus is magnesium, Zn2 plus is zinc, Fe3 plus is iron. So these are all positively charged nutrients that are all attracted to negatively charged soil surfaces. So if we take a picture here and we can see organic matter is here in this area. We can see the different negative charges here that are holding on to these different positively charged nutrients. There's calcium and potassium. And then we have our flat plate-like clay particle right here that has negative charges and is holding on to some positively charged nutrients here as well. And then what we see is that in the soil solution, we also have positively charged particles. And that soil solution is that pore space that has water in it. And then we have this soil surface. So some nutrients are just in solution, kind of moving back and forth freely as they want. But once they tend to get close to those soil particles that have negatively charged surface areas, as they get attracted to them. So they move from soil solution over to the clay particles. But sometimes some will move over there and take place of others, and others will move back. So we tend to see this shifting back and forth until we kind of get to an equilibrium of sorts of nutrients moving back and forth in soil solution and being attracted to the clay particles and organic matter. You can imagine if we have a negatively charged particle here in the soil solution, it's not going to be attracted to these negatively charged soil surfaces. It's actually going to move away. So some negatively charged nutrients are things like nitrate, has a negative charge to it. So if that nitrate is in soil solution, we get lots of water, and these positively charged nutrients are moving next to these clay particles. They can get attached to those particles and they won't move down farther in soil. However, if we have a negatively charged ion here, such as nitrate, when that precipitation comes and that water's moving down the soil profile, maybe below the root zone, there's nothing here that's going to hold on to it because these negatively charged surfaces are actually repelling that nitrogen. And that's why a lot of times we hear about nitrate leaching being such an issue, because nitrate's not held by the soil very well, so it just moves down with that water, and that's why it's really important to manage our irrigation water and hopefully build up our soil organic matter so we can hold more water as well. So here, if we wanted to compare our two kind of extremes of soil textures, our fine textured soil versus our coarse textured soil, and some of these chemical attributes. Our fine textured soil, if we remember right, has lots of clay in it. So clay has has higher CEC, so we're going to imagine fine textured soil is going to naturally have a higher CEC in it. And also, because it has a high CEC, it's able to hold on to nutrients, and the large amount of clay has smaller pores, so it's going to take longer for that water to move down. So you're actually going to have less chance of nutrients moving down and below the root zone where plants can't reach them anymore. And because of that ability to hold on to nutrients, we usually have to add nutrients less often to these soils. So that's our fine textured soil. If we compare that to now our coarse textured soil, we can imagine it's going to be fairly opposite of this, and our medium textured soils are going to be right in the middle of these two. So as we said before, not a lot of clay here, and clay is what has those negatively charged soil surfaces, so we're going to imagine lower CEC. And because larger pores, water goes through faster, not a lot of negative charges on the soil particle surfaces, so nutrients aren't going to be held on to as tightly or as often, so they're going to have a higher chance to be moved down and past the root zone. It's called leaching. And then, because it's not holding on to more, we usually have to add nutrients to these soils more often. So to this point, we've gone over the first few sections here, and now we're going to go into essential plant nutrients. So there are 17 essential plant nutrients, and 3 of them come from what you can see here, from the water and atmosphere. They come from rain, irrigation, oxygen, CO2 in the atmosphere. So we have our carbon as CO2, our hydrogen from water, and our oxygen either from water or from the oxygen in the atmosphere. This is the 3 most abundant nutrients that crops need. We don't think about them very often as nutrients because they're just provided naturally through the water and the air, so we don't think about providing them to plants. However, there are 14 that come from the soil. So 3 out of the 17 essential plant nutrients, 14 come from the soil, 3 come from water and the atmosphere. And here is the long list of essential soil nutrients. So these 14 nutrients all have their associative ion that's taken up by plants. So our nitrogen plant that we can see here uses or takes up the nitrate form, this NO3-, or the ammonium form. Takes up phosphorus in this form. See the negative charge, potassium, sulfur in this form, calcium here. So you can see all these different forms of each of these nutrients that the plant takes up. So if we're looking at those 14 nutrients, we tend to classify them based on the amount of that nutrient that the plant then needs to grow well, produce seed, produce fruit that we can then harvest and eat. So if we break them down in 3 basic categories, we usually have our macronutrients, or also our primary nutrients, and these are the ones that are needed in the greatest amount. And that is our nitrogen, phosphorus, and potassium, or NPK, that you hear probably the most about. And this next group is called secondary nutrients, which is still part of that macronutrient family, still needed in the most abundance, but just less than N, P, and K. And that includes these here: calcium, magnesium, sulfur, and chlorine. And then those nutrients that are needed in the least amount are called micronutrients. It's not that they're not essential, because they're still essential, so if they're limited, they're still going to decrease our growth of our crop, but they're just needed less. So here we see that our iron, manganese, zinc, copper, boron, molybdenum, and nickel are those micronutrients the plant still needs, they're just needed in less abundance. So if we take these 14 nutrients and we kind of see which ones are needed more, which ones are needed less, we have a few other characteristics that are important to know about these different nutrients. And that really has to do with their charge. So we have some that are in the cation form, or they have a positive charge, and that's important because these nutrients are more often retained in the soil. So if we look at those nutrients that are highlighted in green now, these are our positively charged nutrients, or our cations. So when we talk about that cation exchange capacity, these are the nutrients that our negatively charged soil is able to hold on to. So that higher cation exchange capacity, the higher the capacity of that soil to exchange cations, is able to exchange these ones or hold on to these cations that we see here that have this positive charge to them. We can see the positive charge here, here. And we also have anions, nutrients that are in form of anions or that are negatively charged. And as we remember, soil is negatively charged, so if our nutrient is negatively charged, it's going to move down the soil more easily and go below the root because the soil is not holding on to it, because it can't, because it's negatively charged. They actually repel each other. So we see here the red ones now are those that have a negative charge to them. So here we can see we have a negative charge here, negative here, negative here. And nitrogen is actually interesting because it has a nutrient form that's taken up as both a negative form in nitrate and a positive form as ammonium. The biggest issue here is that this ammonium doesn't last very long in the soil, but microbes in the soil like ammonium, and they'll break it down into nitrate fairly quickly. So the most abundant form of nitrogen in the soil is actually nitrate. And we do have a unique nutrient down here in boron that's actually neutrally charged. So there's no positive or negative charge associated with this nutrient when it's taken up by plants. And if we want to know how much of these nutrients we have in our soil, the best way to do that is to test our soils. And we'll go through here in just a little bit of how we can test our soils and what that process is in a coming up video. So if we take a quick look at the outline so far, we've hit these different points. We just finished going over essential plant nutrients. So the next section we'll be moving into is improving soil properties. However, that's kind of a bigger topic, so we'll save that for a video here coming up really quick. I'd just like to thank you for joining me today to talk more about our soil biological, chemical properties, as well as essential plant nutrients. And as always, if you have questions, feel free to reach out to me and I can hopefully better explain some of these different concepts. Thank you.